Good morning, students. In the previous class, I was telling you about this class B push-pull operation, and we were seeing this particular circuit. It is called complementary symmetry push-pull circuit because we are using one NPN as well as one PNP. And as you can see, there is no static power consumption for this circuit at all. Only when the input is there, then the NPN will conduct for the positive cycle, PNP will conduct for the negative cycle. That way, once when NPN conducts, the current flows. Let me annotate. When NPN conducts, the current flows in this direction, and when PNP conducts, as it is already indicated, current flows in the other direction. So that way, even the input is AC, output is also AC across the load. Now, this point is the ground. Wherever these two power supplies are connected, that is the ground, and the load is connected to the emitter shorts. Wherever two emitters are connected, at the same point, load is connected. So now, as I was telling in the last class, you may wonder where is the amplification happening here now when the input signal is making the transistor to turn on. Here the amplification will happen only when these VCC values are much larger than the input signal. As we already know, in the case of large signal amplifiers, the input signal will not be in millivolts, it will be in volts. So let us say the input voltage is now around 10 volts peak to peak. If it is 10 volts peak to peak, let us say, that means it is 5 volts each peak. If it is 10 volts peak to peak, we can choose this VCC to be, let us say, 25 volts. And the lower VCC also 25 volts. Effectively, we will have totally 50 volts swing. And that is how. Each peak is now 25 volts. And the input was 5 volts peak. So for a 10 volts peak to peak signal, we will get around 50 volts peak to peak signal, that is 5 times the voltage gain. If you want a larger gain, we can have a larger value of VCC. But the only disadvantage here is the crossover distortion. That means until the input signal reaches 0.7 volts, the upper NPN will not turn on, and until the input signal reaches minus 0.7 volts, the PNP will not turn on. That time, both these transistors are off. And when they are off, there will be no output there. That is called crossover distortion. Now, with this particular circuitry, we will always have this crossover distortion. Because we have this zero crossover. During the zero crossover, both transistors are off until the input signal reaches their VBE. So, how to overcome this crossover distortion, if at all we want to overcome? That we will see in the next slide. Now, this is called class AB operation. To eliminate the crossover distortion, a slight forward bias needs to be applied to each base emitter junction. This means that the Q point gets located slightly above cutoff. In the circuit which I am showing you now, the Q point is at cutoff region. That means when the input signal is absent, both the transistors are off. That means the Q point is situated in the cutoff region. Now, to overcome the crossover distortion, we will have to apply a slight forward bias for each of the transistors. Now, when we apply a forward bias, then there will not be a 180-degree cycle for each transistor. Unlike the previous operation called class B, when we apply a forward bias, each transistor will be slightly conducting, and then the conduction angle of the amplifier will be above 180 but below 360. In class A operation, the conduction angle was completely 360 degree. In class B, we have seen it is only 180 degree. But in this class AB operation, we want to overcome the crossover distortion. For that purpose, we apply a slight forward bias, and now the conduction angle will be slightly above 180 degree. So in general, an ICQ or a quiescent current of 1% to 5% of the IC sat is enough to eliminate the crossover distortion, which means we need not really bother much about keeping the Q point in the middle of the load line. If it is in the middle of the load line, that is class A only. Now, if it is at the end of the load line in the x-axis, then it is class B. If it is completely in the cutoff region, it is class B. If it is exactly in the middle of the active region, that is class A. Now we are slightly keeping it above cutoff, but we are not keeping it at the middle of the load line also. We are keeping it below. So a quiescent current of about 1% to 5% of the IC sat is enough to eliminate the crossover distortion, because we want to keep this transistor slightly in the on condition. Because of the slight forward bias at the base, the conduction angle will now be slightly greater than 180 degree, and hence this operation is referred to as class AB. You can see these examples. These are the examples of class AB amplifiers. At the left side, you can see a voltage divider bias network where R1 and R2 are part of the voltage divider bias for the upper transistor. Again, it is the same case with the lower transistor, but we apply the input at the junction here. Let me annotate. We will be applying the input here. Okay. So along with the capacitor, we can apply the input this way. Okay, this way through a capacitor, we can apply the input. And when you apply this input, already this, because of the R1 and R2, you can see upper side there is VCC, lower side there is ground. Because of these resistors, the transistors are kept slightly in the on condition. They are in the active region, but very near to the cutoff region. That way we can choose the values of R1 and R2. Now when we apply the input signal, when the positive cycle is there, gradually the upper NPN will turn on, and when the negative cycle is there, gradually PNP will turn on. At that time NPN will be off. So we can take the output here at the junction. At the output, at the point where emitters are connected, we can take the output again by connecting a coupling capacitor there. So the input signal is applied at the junction of R2. Another way to keep this transistor slightly on is by using the diodes. Here also you can see the same thing by using the diodes, because each diode's drop is approximately equal to VBE. That way we can use only two resistors and we can connect two diodes here. And by default, the transistor will be on now. Now when we apply the input signal, gradually whenever there is a positive cycle, this diode will be reverse biased because of the positive cycle. When the diode is reverse biased, there will be more base current flowing through this R. Otherwise, the base current is diverted towards the ground. Now you can see whenever there is a positive cycle here, and this diode will be reverse biased. Because of the reverse biasing of this diode, this R will supply current to the base of the transistor, and NPN will turn on. When NPN turns on, gradually here also you can have a rise, because VCC is getting connected to output now. Similarly, during the negative cycle, what happens is, during the negative cycle, this gets turned off. The lower diode turns off, and then this PNP conducts this way. You already know that in the case of PNP, base current goes out of the base. So PNP conducts this way, and that is how at the output the negative cycle is reproduced. Now if you want to have a larger amplification, we can increase the value of VCC. So in this way we are keeping both the transistors slightly on, and when the input signal is applied, they will turn on and turn off accordingly. And here the conduction angle is slightly greater than 180 degree. That is why this is called as class AB. You can see one more example of class AB operation here. This is called quasi-complementary push-pull circuit with Darlington transistor. It is again push-pull but quasi-complementary. In the sense, you can see Darlington transistors. You already know that the Darlington transistors will have larger beta. I hope you have already seen this in the lab experiment. Now, if the upper transistor is having beta 1, lower transistor having beta 2, the emitter current of the upper transistor is the base current to the lower transistor. That way, total current gain will be beta 1 into beta 2. So, if the upper transistor's beta 1 is 100, if the lower transistor's beta 1 is 100, then total gain is 100 into 100 is 10,000. That is what is the Darlington transistor. At the upper side you are seeing a NPN Darlington, at the lower side you are seeing a PNP Darlington. Now you can see to the NPN through this VCC1 through R1 base current is supplied. Through the PNP through this R2 the base current is supplied through the VCC2. And there are these emitter resistors here. At the junction we can connect a load. Here he is showing that AC load when speaker is disconnected, we can connect a 4 to 16 ohm speaker across this. Now this AC load is connected when the speaker is disconnected. The purpose is that there should not be a sudden no load to full load swing at the output. That will lead to distortion in the beginning when the load is connected. To compensate that, they can connect a general lesser load at the output. That is where 122 ohms and 0.22 microfarad are connected here. Now across them 4 to 16 ohm speaker also can be connected. Now you can see when we apply the input signal in the positive cycle, what happens is because of the positive cycle now current to this base of this transistor will increase and it will come towards the middle of the load line and more current flows in this direction. Let me annotate. When we apply a positive cycle, more current flows in this direction. And when you apply a negative cycle, accordingly, the base current for the PNP is going to increase, and that is when from the same VCC2 we have, VCC2, this way only. So, in the negative cycle, this will conduct in this manner, PNP will conduct in this manner. And that is when you can see the ground is here, the same ground is here. And that means the load is connected in between these 2 points. Load is connected in between these 2 points. If you ignore the AC load when speaker is disconnected temporarily, now what we can say is wherever I have marked here, between these 2 points. Let me write it neatly. So between these 2 points, we can have the load getting connected here. Load is nothing but a speaker. So now in the positive cycle current flows in this direction and in the negative cycle current flows in this direction. You can see the directions of the current are reverse in both cases. So that is how when the input signal AC is applied, it is switched on and off, or switched on, so to say, by means of the upper Darlington as well as the lower Darlington. And if we choose a larger value of VCC, then naturally we will have a gain. This is a quasi-complementary push-pull circuit. Why do we say it as quasi-complementary? The earlier push-pull circuit which I showed you, which was class B with the crossover distortion, it was complete complementary. In the sense there was a NPN and there was a PNP and there was no bias for those transistors. But in this case you can see there is a slight base bias for the transistors. Let us see one more example of the circuit now. Quasi-complementary push-pull circuit with Darlington and Sziklai pairs. You can see now in this circuit there is a variable resistor at the base, unlike the previous case. I will show you. In the previous case we have this R1 and R2 and we have this RE as balancing resistors, then we have a balancing load also. Now you can see in this case at the base there is this R2 and we have the C1 and C2, and you can see input is directly connected to the first terminals of C1 and C2, and the C1 is connected to the upper NPN Darlington, C2 is connected to the lower, it is called Sziklai pair, it is not Darlington now. In the previous case it was Darlington only, PNP, you can see this here. In the present case you can see one PNP and then one more NPN, and you can see the change in the connection of the load. In the previous case we had these two VCC, one for upper Darlington NPN, one for lower Darlington PNP. We had two exclusive power supplies. Now in this particular circuit you can see only one single VCC. That is the advantage of using this Sziklai pair. It is also called as feedback pair. You can see the difference between the Darlington pair and the Sziklai pair is, in the Darlington pair both transistors are of same type, either NPN NPN or PNP PNP. Now in the Sziklai pair you can see PNP NPN. In the same Sziklai pair NPN PNP is also possible. So here how the circuit functions is, you can see when input signal is applied, now in the positive cycle the upper Darlington transistor conducts and from VCC current flows to the load in this manner. When Darlington conducts, current flows to the load in this manner. Now in the negative cycle what happens is, because in the case of PNP always current has to flow out of the base. In the negative cycle this PNP is conducting. This PNP is conducting in this manner. And at that time the PNP is supplying the base current to the NPN now. So now current flows through the load in this manner, in the reverse direction. Earlier the current was flowing from VCC to ground in this way, and the direction of current, as I have shown you at the upper side, it was from, let us say, upper side of the load to the lower side of the load. Now in the negative cycle current is going in the reverse direction through the load, through this capacitor. Now you may think, why again it is all ground only, ground to ground how can current flow? You may be thinking that from ground to ground how can current flow? But you have to remember we are discussing AC now. When we are discussing AC, in the earlier case it was a positive cycle. Positive, because of the input's positive cycle, that positive cycle's current was flowing. Now automatically whatever is the storage of energy at the load, that will be discharged in the other direction. That itself is AC. So in the positive cycle energy is supplied to the load, and in the negative cycle energy is taken out from the load. So you need not think that it is ground to ground how can current flow. It is not that way. Always visualize the load as either a loudspeaker or any other dynamic device there. So there is a change of direction of energy flow in the load. That is how this is working in the class AB operation. And what for is this R2? R2, using R2 we can actually balance the point at which upper transistors will conduct and the lower transistors will conduct in accordance with the input signal. That is how a variable resistor is given. Dynamically we have to slightly vary. Before applying the input signal we will have to vary this in such a way that both of these will be slightly conducting. And when we apply positive and negative cycle, automatically whatever I have told till now about the functioning, that is going to happen. So this is another example of quasi-complementary push-pull circuit. This also comes under class AB only, but the only difference is that instead of the Darlington pair we are using the Sziklai pair, which is a combination of PNP and NPN. Now in this case we are using this type of Sziklai pair. Actually Sziklai pair one more type is also possible. This way also it is possible. You can see here now. Whenever NPN conducts, it will conduct in this manner. Let us say a signal is applied at the base of NPN. NPN conducts, NPN from collector to emitter current flows, and when collector to emitter current flows, actually current is going out of the base of the PNP. So now the PNP also conducts in this manner. Now through the PNP also current is flowing out, and through the NPN's emitter also current is flowing out. So net current will be the sum of this current and this current. Now this is also Sziklai pair only, but connected in a slightly different way. There are such multiple connections possible. So let me proceed now. Let us have an exercise now. Calculate the input power, output power, power handled by, I am unable to see this because here, output power, power handled by each transistor, and the circuit efficiency for the circuit shown for an input of 12 volt RMS. Now there is no change here as such. This is same as our class B's operation. Let me remind you by showing you the slide where we have formulae of class B. This is just to show you. Input power is VCC into IDC. What is IDC? IDC is 2 into I peak divided by pi. And output AC power is VL squared RMS divided by RL. What is VL squared RMS? VL squared RMS is VL peak divided by root 2. Actually, VL RMS is VL peak divided by root 2. And when we square it, we get 2. Now, VLP divided by VLPP divided by 2 root 2. When we square it, we get VL square PP by 8RL. That is VL square P divided by 2RL. So, this is the DC power, VCC into IDC. This is the AC power, VL square RMS divided by RL. And then we had this maximum power efficiency is VL peak divided by VCC into pi by 4. So when VCC is equal to VLP, we used to have the maximum efficiency as 78.57%. Now the power dissipated by each transistor is P2Q is given by PIDC minus P0AC. And each transistor will have half of the power dissipation across it. So this is the formula which we used in class B power amplifier. It is the same formula which we are going to use in class AB also. The only difference between class B and class AB is that we are slightly keeping the transistor on, that's all. Otherwise there is no major difference. Only thing is the circuit configurations are slightly going to differ, but the analysis of the circuit is going to be the same. So these are the formula which we are going to use for the solution of the problem now for class AB. So remember, PIDC is VCC into IP into 2 by pi. P0 AC is VL square P divided by 2RL. P2Q is PIDC minus P0 AC. So using these formulae, let us solve that exercise. I am showing you the answers now. Before that, there is this diode here and there is this R3 here. Now the diode is also there. Because now in this case, it is not a Darlington transistor or Sziklai pairs usage. Now they are single transistors. So as far as VBE is concerned, there can be a difference between NPN and PNP itself. That is one point. Second point is always the mobility of charge carriers in case of PNP is lesser when compared to that of NPN. You might have come across this term in physics. There is some term called mu n and there is one more term called mu p. Mu n corresponds to mobility of electrons and mu p corresponds to mobility of holes. Mobility of holes is always lesser than the mobility of electrons. That is because holes actually do not exist as such. Only electrons exist. The vacancy of electrons is called as holes. So if the hole has to be filled, any electron has to come there and occupy that particular position. So naturally, hole mobility is lesser than electron mobility. Now to compensate that, we have this R3 along with the diode here. So that if there is a difference between the NPN and PNP, then gradually by slightly varying the value of R3, we can keep both these transistors slightly on. That is the idea. But in the previous circuit which I have shown you, in this circuit it is not necessary. The diode is not necessary. But in the previous circuit, we had these two diodes. There were single transistors, but we had this R and R. In this circuit, the diode is not necessary. Why? Because we are giving enough supply by means of this R1 and R2. But in this circuit, we are using this middle transistor because we are using a Sziklai pair here. And because there are two transistors each, again it is beta 1 into beta 2. So that diode was not necessary. But in this circuit, we have this diode necessary because of the single transistors. So by using the formula which I showed you a few minutes before, we will solve this exercise now. VIP is 12 into 1.414. That is VCC into IDC. IDC is 2 into IP divided by pi. So how IP is calculated? We have these 12 volts, RMS as the input. So that way, we have this VIP is 12 into, actually VIP itself is calculated here. VIP is 12 volts RMS into 1.414, that is root 2, that is 16.97 volts. Now the peak voltage at the load is 16.97 volts only because voltage gain is 1 here. Now how do we say the voltage gain is 1 here? Can anybody tell me how do we say that the voltage gain here is 1? Anybody can answer? Okay, nobody is responding. The answer is, this is an emitter follower circuit. You can see when we apply an input signal here, we are taking output at the emitter. Even for the negative cycle, we are taking output at the emitter of PNP. You can see that is a VCC plus 25, VEE minus 25. So this is now an emitter follower. As it is an emitter follower, you already know that the emitter follower's voltage gain is unity. So we take the load voltage here as the same as the input voltage. Now if the load voltage is same as the input voltage, you may think what may be the use here? The use is we can pump a larger current. Even though the voltage gain is not there, current gain will be there in this case. And because of the current gain, power gain will be there in this case. That is the idea here. So VL peak is same as VI peak, that is 16.97. We have obtained VI peak by multiplying RMS input by root 2. Root 2 is 1.414. Now IL peak is what? IL peak is 16.97 divided by 4 ohms. Here the resistance is given. Peak value at the load, peak value of voltage at the load divided by the resistance is 4.24 amps. Now IDC is, as you already know, it is 2 into 4.24 divided by 3.14. So it is IRMS divided by pi. 2 into IP, not IRMS. 2 into IP divided by pi. That is 2 into 4.24 divided by 3.14. Now ILP is this 4.24 amperes, right? So IDC we get 2.7 amperes. So now DC input power is 25 into 2.7. VCC is 25 volts and into IDC is 2.7. VCC into IDC is 67.5 watts. And output power AC is now 17 square divided by 2 into 4. It is 17 squared. P0 AC is 17 square divided by 2 into 4. That is 36.13 watts. So we get the efficiency as 36.13 divided by 67.5. Actually this 17 I let replace by 16.97. I have used the round figure here. Okay. Later on I will make that change. This has to be 16.97 whole squared. It should be. I forgot to exactly put the value. I have put the round figure value here. That's all. But it will not make much of a difference. Here it is only 0.03 volts. So it will not make a great difference there. Later on anyhow I will correct it. So output AC power is 16.97 whole square divided by 2 RL, that is 36.13 watts. So the efficiency is 36.13 divided by 67.5. Output AC power divided by input DC power, that is 53.53%. You can see it is more than class A. Class A can be having maximum 50%. Now here it is more than class A because now this is class AB. And the quiescent power is nothing but input DC power minus output AC power divided by 2, that is 67.5 minus 36.13 divided by 2, that is 15.69 watts. So each transistor here, Q1 and Q2, they will be handling 15.69 watts in this case. We should choose the transistor which can handle at least up to 32 watts now. This is approximately 16 watts. So each transistor must be rated to the maximum power of 32 watt. Because in general we choose double the power of the normal power which the transistor is handling right now. So this is how this exercise is solved. Let me proceed. Now the exercise 10 is, for the previous circuit, calculate the maximum input power, maximum output power, input voltage for maximum power operation, and the power dissipated by the output transistors. Let me show you the slide where we had discussed the maximum power. Yes. In class B, we had discussed this maximum power considerations, where maximum P0 AC used to be Vc square divided by 2 RL. Maximum input power is 2 into Vcc square divided by pi RL. This we had discussed in the previous class. Now the maximum power dissipated by the output transistors remain the same, that is P2Q. But when we apply these maximum power formulae, we get maximum P2Q as 2 Vcc square divided by pi squared RL. Now these are the formulae which we have to use for the present exercise. So let me go to the present exercise. Yeah. Now to calculate the maximum input power. Maximum input power is 2 into 25 squared divided by 3.14 into 4. Applying that formula, we get 99.47 watts. Now the maximum output power is, again VCC here is 25. 25 square divided by 2 into 4, that is 78.13 watts. You can see in the input power the pi term is coming into picture. Now the maximum efficiency you can directly calculate. 78.13 divided by 99.47, we are getting about 78.55%. It is same as our class B only. Class B also used to have the maximum theoretical efficiency as 78.57% as per the formula derived. It is almost the same here. Input voltage for maximum power can be 25 volts only, because VCC in this case is 25 volts. Now lastly, P2Q, or the power dissipated by the output transistors. Here he has not asked the individual transistors, he has asked the total power dissipated by the output transistors. That is 99.47 minus 78.13, that is going to be 21.34 watts. So this is about the exercises regarding the class AB circuits, where the formulae are almost going to be the same as class B circuits. You will have to work out and you will have to remember these formulae. Now, before proceeding to class C, let us discuss a little more about distortion. Let me admit the student. We have seen class A, we have seen class B, then we have seen class AB. The sequence was AB was discussed after class B because class AB is nothing but a slight variation in class B itself. And the effort here was always to increase the efficiency. We have seen that in class A efficiency is lesser. So in class B we wanted to have a higher efficiency. And in class B we have already seen one type of distortion called crossover distortion, because that was happening during zero crossover. And now let us define what is the basic meaning of distortion. A pure sinusoidal signal has equal amounts of variation in positive and negative cycles. This is already known. But if any signal varies over less than the full 360-degree cycle, then it is called as distortion. Means, in this 360-degree cycle, if the amplitude does not follow the continuous nature, and even if the frequency does not remain constant in this 360-degree cycle, then that is called amplitude distortion and frequency distortion. There are two distortions here. Both can happen with our power amplifiers. In our small signal amplifiers, we did not bother much about the distortion. Why? We were applying a very small signal there and we were getting a voltage gain there, and we did not bother about distortion. That was always in general faithful amplification, because the transistor always used to be in the middle of the load line. But in the case of these power amplifiers, we have seen in class B and class AB, the Q point is nearer to cutoff region. So distortion is bound to occur in one way or the other because of the non-ideal behavior of the devices. So amplitude distortion can occur due to the non-linear device characteristics, and frequency distortion can occur due to the difference in frequency response of the circuit elements. In module 3, we have seen how frequency response also remains non-ideal because of the internal as well as external capacitances and resistances. So there can be amplitude distortion also, there can be frequency distortion also. In the next slide, I am going to show you the example. You have already gone through the Fourier series. It is discussed in the maths courses also. It is discussed in the signals and systems course also. The Fourier analysis defines the signal as the fundamental frequency and its integer multiples as the harmonics. This scientist Fourier, or the mathematician Fourier, is one of the greatest contributors to the engineering field in terms of the signal analysis, because he gave the idea that any complex waveform can be represented by means of a fundamental signal and the other frequency components. All the other frequency components are also called as spectral components. For example, right now when I am speaking, my speech is not a pure sine wave. My speech is basically a complex wave. Let me write a small waveform here. When I am speaking now, my speech will be like this. Sometimes the amplitude will increase, sometimes the amplitude will reduce, sometimes the frequency also will change, because my vocal cords are producing vowels and consonants are produced when we use our tongue and teeth and lips to pronounce a particular alphabet. So speech is basically a combination of pronunciation of so many alphabets. The alphabets are combined to form words, words are combined to form sentences, sentences are combined to form paragraphs, Paragraphs are combined to form a page, and pages are combined to form a book. That is how it is in the case of written book. Similarly, here also, whenever we pronounce a particular alphabet, and that alphabet, many alphabets combine together to become a word, many words combine together to become a sentence. In that way, when the speech is produced, anybody's speech cannot be a pure sine wave at all, because a pure sine wave cannot contain any information, it does not change. Anything which does not change does not contain information as such. So you can see my speech waveform can be in this way. Whenever you come back to college, I would advise you to come into AEC lab, and there in your spare time you can connect a microphone to an amplifier, and the output you can see in the oscilloscope whenever you speak, how your speech waveform appears on the screen of the oscilloscope can be verified or can be seen, can be observed. So I have written a waveform. You can see this is a complex waveform. Complex in the sense it is not having a continuous smooth variation. There are abrupt variations both in amplitude and in frequency. Now Fourier gave a great tool here by representing this complex waveform in terms of a fundamental frequency and its integer multiples. Let us say, for example, this is my speech waveform, and let us say based on the construction of my vocal cord, we can imagine that the fundamental frequency of my voice is around 400 Hz. Generally, male voice will be between 300 to 600 Hz. Female voice will be between 600 to 900 Hz. And the children voice will be from 900 to 1200 Hz. That depends on the size of the vocal cord. In the case of children, the vocal cord is really very thin, so any thinner object can vibrate faster. That is how the frequency of the children's voice is larger, a range of around 900 to 1200 Hz. In the case of females, when they grow up, the vocal cord slightly thickens. With all of us, when we grow up, the vocal cord slightly thickens and the frequency now reduces. In the case of females, it becomes 600 to 900 Hz now. In the case of males, when they undergo puberty, the vocal cord actually becomes more thicker in the case of males, and the voice becomes slightly harsh in the case of males. That is how the nature is making males to protect themselves against the situations of danger by means of using a harsh voice. That is how nature had done human beings that way. In the prehistoric ages, male apes used to go out looking for food, and female apes used to stay inside the cave taking care of the children. That is how nature made an experiment with the males. And as human beings are the evolutionary organisms of the apes, even now it remains in male human bodies. Even though now we are not staying in caves anymore, but nature takes its own time to change these things. Maybe a few centuries, maybe a few millenniums. We don't know. So that way, female voice is between 600 to 900 Hz, whereas male voice can be between 300 to 600 Hz. I am considering my voice frequency is fundamental frequency around 400 Hz. Now using 400 Hz and using its integer multiples as harmonics, that means using 800 Hz, then 1200 Hz, then 1600 Hz, then 2000 Hz, that way it can go on till infinity with the different constants. Now the complex wave which I am showing you on the screen, this can be represented by means of this fundamental frequency 400 Hz along with its integer multiples which are called as harmonics. They can be 800 Hz, 1200 Hz, 1600 Hz, 2000 Hz, it goes on that way. And all the constants of these harmonics can be in the decreasing order. That means 400 Hz will have the maximum constant when it is expressed in the mathematical form, and other frequencies will have constants in the decreasing order. That way Fourier gave a great tool, a mathematical tool to represent the signals. That is called Fourier analysis now. Now, using this Fourier analysis, the signal can be represented with the fundamental frequency and its integer multiples. The integer multiples are called harmonics. Therefore, the distorted signal contains the fundamental frequency along with the second harmonic, third harmonic and so on, but with reducing amplitudes. I showed you now a complex waveform, but in the case of our amplifiers here, when we have a continuous waveform, let us say, for a siren, let us say, we put a fundamental signal only, we wouldn't put a complicated waveform, right? The complex waveform is applicable in the case of class A amplifier, where it is meant for audio amplification. Now, in the case of a siren, it need not be a complex waveform. It can be a combination of only two frequencies or maybe a single frequency at times. So, the distorted signal, if at all in the siren, if the signal gets distorted because of the amplifier now, the distorted signal contains the fundamental frequency along with the second harmonic, third harmonic and so on, but with reducing amplitudes. So, the percentage of the nth harmonic distortion or percentage of dn, if you have to say, second, third, fourth, like that, that is the amplitude of an divided by amplitude of a1 into 100%. What is this a1? a1 is the amplitude of the fundamental signal, fundamental frequency. an is the amplitude of the nth harmonic. Now, there is something called THD, total harmonic distortion. Total harmonic distortion is given by square root of d2 square plus d3 square plus d4 square, like that it goes on, into 100%. Now, you can see d1 square is not at